So by a bottleneck here, I'm referring to some kind of structure in the Hamiltonian that prohibits families of algorithms from doing well. This is kind of going to be a generalization of a classical bottleneck argument. This will all be defined much more in the coming slides, of course. So let's start with what is a thermal state. It's defined like this. I'm told they're useful for all sorts of things. You can, if you're a chemist and you want to prepare something close to the ground state to measure its ground state energy, maybe you do quantum phase estimation, but then you need a good state that has overlap with the ground state. So then how do you prepare that? Well, it's not so obvious. The benefit of preparing a cold Gibbs state is you don't need kind of an initial state with good ground state overlap. It appears in quantum STPs, it appears in, you can kind of throw this at any optimization problem. Maybe you have like a random KSAT and you want to try to find satisfied solutions. You could try just cooling down. You can do like classically a Metropolis-like algorithm. There are all sorts of things you can use this sort of primitive for. Things we're going to answer in this talk. So a question you might have is, this is a quantum algorithm. Maybe I should use it for my classical optimization problem. You know, it's doing this kind of off diagonal things. Is that a good idea? Is it not? I think that was an open question. We'll answer that here. Or maybe you have a non-commuting Hamiltonian, you understand its mixing time. The kind of existing techniques people have for understanding mixing times are largely restricted to commuting Hamiltonians. But if you have a non-commuting Hamiltonian, there's kind of a shortage of tools to know how fast does it mix. We're also going to provide mixing time bounds on non-commuting Hamiltonians here. And then maybe you don't care about Gibbs states, which is also fine. But do you like lower bounds? And you want to know, are there tools here that I should be thinking about for new lower bounds? And one thing that I am very excited about this work is it's kind of the first translation I know of these overlap gap property sorts of tools that people use to provide lower bounds for stable algorithms. So if you have anything classically that's like local or low degree, oftentimes you can produce lower bounds that are tight with algorithms like message passing algorithms using these techniques. And this represents a quantum generalization of some of that, but applied here only to this family of algorithms of Gibbs algorithms. But I hope that ideas can be useful elsewhere for kind of local quantum algorithms or low degree or other stable quantum algorithms. So, okay, let's look at how to prepare this Gibbs state and understand what I mean by a Gibbs sampler formally. So we will try to write down a quantum algorithm for this. I'm going to kind of summarize this recent line of work done by Anthony Chen, Andres Gillian, Les Castellano, folks at Berkeley, Lin, on preparing Gibbs states. So the basic question is, how do you prepare a Gibbs state? And they first ask, well, how does nature prepare a Gibbs state? Maybe we'll start there. And the answer is, well, you have this very nice picture where if you put a state in a refrigerator, some system in a refrigerator, physicists tell us that this is exactly the same thing as coupling into a bath. Where here, what I mean is that you have some kind of system Hamiltonian, some bath Hamiltonian, and you start with this state that's like a product state between these two things. And then you time evolve it under this Hamiltonian, where lambda here is some coupling that you make very weak. You do this for infinite time, and eventually, or there's the mixing time, of course, associated with this. But in the t goes to infinity limit, you'll prepare a system that has the same temperature as the bath. Your bath is large enough, and you wait long enough. This kind of coupling Hamiltonian, this interacting Hamiltonian has these AA operators. These are permission operators that you should think of as local operators. Maybe they're like local Paulis or something. And they're going to be called jump operators. So if you hear me saying jump operator, I'm referring to kind of a permission local operator like this AA. Yeah.
Why is there no like sum with B, but there's a sum with A?
Oh, sorry, that's supposed to be BA, not BB. I got carried away with my A's and B's. A is just the index, yeah. So now how do we do this on a quantum computer? Well, you can try to do exactly the same thing as nature did. So you're just going to look at the system half of the system in bath and try to write down open dynamics that describe this. And so Lindblad wrote down what open dynamics looks like this. you have kind of a first term where G is a Hermitian matrix that gives you like a coherent time evolution. And then you have a second term that gives you your dissipative dynamics that move you towards, in our case, it'll be a fixed point. And so we just have to ask, how do we choose G and LK to do what nature was doing? Surely that's going to be an algorithm that works. And so what we're going, it turns out that in the coupling to a bath, what in the actual, if you evaluate what this Lindbladian is, the coherent term drops away. It doesn't, it's zero. And you only have to find these kind of L sub k dissipative Lindblad operators. Okay, so how does this bath coupling LK operators look like? We need a few ingredients. We have our system Hamiltonian. I'm going to write it in its eigenbasis here. And then we have this set of jump operators, these like local pallies or something perhaps. And there are two things you have to define. The first one is what we're going to pay attention to, but the second one is worth mentioning. So you have these A sub nu superscript A operators. They're basically your jump operators, but written in terms of differences between eigenvectors. So this is what's going to be underneath all of the modern Gibbs sampling algorithms. So this difference of E sub I minus E sub j, the set of those differences is known as the Bohr spectrum. And what this does is it just kind of gives you hops from one energy to another. And these A nu A operators, it turns out, are going to be our Lindblad operators. But we're going to have to rescale them by some scalar, which satisfies something called detailed balance, which I won't get into since it won't actually matter for the lower bounds. Yeah, your Lindblad operators are given by just these A nu A operators, essentially. And your temperature is set only by this gamma function. So if you evaluate this coupling system to bath, this is the Lindbladian you're going to get. It's just going to have your gamma times A nu A's. So okay, now you want to do this on a quantum computer. Well, there are all sorts of ways to do Lindblad evolution. These algorithms usually need things like block encodings of your Lindblad operators. And so now we're stuck with an operator that looks like this if we want to try to realize it on a quantum computer. That's a little gnarly to construct. We don't know the eigenbasis of our Hamiltonian. We can't, like, that would take forever to figure out how do we construct this. And so yeah.
So can I ask a bigger picture question? Like, how does these AAs relate to Hamiltonian? Because like somehow, you know, the Gibbs state is for Hamiltonian,
right,
but these AAs were sort of arbitrary.
They're arbitrary, yeah. So what you're going to want to do is just pick like for instance, the set of all one local pallies is going to work.
And so is the reason we are expecting to get the Gibbs state is because you're using these A nus, which have some information about the eigenvectors.
Exactly. So if you were to think of like a classical Metropolis-like algorithm, the AAs are just going to be like flipping one bit. You can do pretty much any kind of local operation, but yeah, you'll eventually converge. So the insight of the recent line of papers is that what you can do is just choose your gamma function in a clever way. You can choose it to be both something that satisfies detailed balance, either exactly or approximately, and something that's fairly smooth. And I'm going to be very vague since I'm not going to talk about the algorithms more, but you can prepare instead of individual NUAs, it works, it's good enough to sum over nu and prepare some larger object as your Lindblad operators. Now you have to introduce a coherent term, but the coherent term is also written in a very similar form. And so your entire algorithm will depend only on things. It'll be like an algorithm that's a degree 2 polynomial, degree 2 polynomial in NUAs. So it's going to be, this is also going to give us a hint as to what kind of locality we are looking for in the algorithm, where the Lindblad operators are just written as sums of NUA. Okay, so that's all I'm going to say about the upper bounds for Gibbs samplers. And it's this class of algorithms that we're going to be lower bounding.
You say something about how fast this is?
When you say how fast it is,
There's a bunch of parameters here, like the capacity age and the temperature, etc. Like how much time would this method cost you to prepare a good approximation to rho beta?
yeah, so it's going to, I think they scale either as like beta or beta squared. They're like the relevant time scale, it's all polynomial in terms of like epsilon, beta, and things like this. The relevant time scale that usually hurts you is the mixing time. And so that's what we're going to focus on.
Because this is a QMA hard problem, right? So in general, this will take you exponential time to approximate good.
Yeah, the QMA hardness is going to be in like, it will give you an exponential mixing time. But doing this is all very kosher. Yeah. Okay. So let's define mixing time. What mixing time is just a statement of informally how long it takes you to get close to the thermal state, starting from any initial state. And in practice, you can define it with like an arbitrary constant there, just saying two states. I'm going to start randomly with sigma and sigma prime, arbitrary states. They're going to get closer and closer together as I get towards the mixed state. So there'll be some characteristic timescale associated with that. And that timescale is the mixing time. What I'm going to provide lower bounds for here in this talk are, I'm just going to say Gibbs sampler. But when I say Gibbs sampler, I really mean something like what we just saw. So I'm referring to a family of algorithms where there are Lindbladians, and all of the Lindblad operators are constant degree polynomials in the A nu A operators. And that this Lindblad map has like a unique fixed point at the thermal state. The uniqueness of the fixed point is implied by detailed balance. I don't actually need detailed balance, just this kind of more general condition is sufficient. So this is the whole setup of this talk in some sense. And so now we can maybe get into some of the new ideas. Any other questions about the setup?
Like, you mean for all sigma and sigma prime?
Yeah.
The algorithm is just like do some sort of converging thing that will eventually converge, and all the steps in algorithm are efficient, but you don't know how long it takes.
Yes, there's one more thing that we'll need, one more assumption, when you are dealing with non-commuting Hamiltonians. For our results for non-commuting Hamiltonians to hold, we're also going to need some kind of geometric locality. And so this is a nice feature of the modern Gibbs sampling algorithms. It also is perhaps one of the reasons that they're somewhat efficient to run, which is that if I have a Hamiltonian that lives on a lattice, which most physical systems do, then the kind of Lindblad operators that I get out are quasi-local. Don't worry if you don't know formally what quasi-local means. We'll get to it later. But just a caveat, for non-commuting Hamiltonians, we're also going to need this assumption of the Gibbs samplers. Okay, so roughly speaking, what are we going to show here? I'm going to show that there's like a general technique, which we'll call a bottleneck lemma, that says that your mixing time is going to be super polynomial. And then we're going to apply this bottleneck lemma to several systems, families of systems. We'll show that if you have any kind of classical Hamiltonian that's hard for Metropolis-like classical algorithms, it will also be hard for a quantum Gibbs sampler. Like being able to do things in the off-diagonal direction of your jump operators never helps. We're going to also show then, outside of classical Hamiltonians, you can write down other commuting Hamiltonians, and we're going to show mixing time lower bounds for those. But I'm actually going to skip that result in this talk because I think it was partly known in the field. There is a result we're going to show, like we could show for a good code that the mixing time is exponential in n. There's an existing result that showed that it's exponential in root n, but I think the proof would actually work if they just used a different code to get to exponential in n. And so the most interesting thing that I'd like to spend time on is, I think, this transverse field Ising model, where we have a mixing time bound for non-commuting Hamiltonian, since that's really different. Yeah.
Like code Hamiltonians are easy to find ground states.
Yeah, so
Using the wrong algorithm or?
yeah, these are lower bounds for this family of Gibbs samplers. It's not going to be a lower bound for any Hamiltonian or any algorithm. Yeah. I guess when your Hamiltonian has so much structure like a code Hamiltonian, you can kind of think very hard or very little and write down an algorithm to prepare a ground state. But for things like random k-sat, the best known classical algorithms are things that look like these local, like walk sat or maple sat or something. And so that's where lower bounds that apply to all sorts of algorithms in this family are a pretty good idea. Yeah, so I'll just talk about the first and third results this time. Okay, so now let's try to say a bit more formally what a bottleneck is here. So let's think about only a classical bottleneck to start with. This is going to be maybe familiar stuff. So let's say I have a Hamiltonian that's just defined over bit strings, diagonal on the computational basis, and a classical Markov chain that has associated with it some aperiodic irreducible transition matrix that satisfies two things. It has a stationary distribution, that's the Gibbs distribution, and it's local, like it flips at most one bit. This is kind of how your standard Metropolis Hastings algorithm looks. So now we want to write down what a bottleneck for this algorithm would be. And pictorially, it looks something like this. We're going to have the space of bit strings divided into disjoint regions A, B, and C, where under the Gibbs measure, the stationary distribution, A and C both have constant support. And then there's a bottleneck region B that has, I'm just going to make it exponentially small over here, support. And the locality of the sampler, where it can only flip one bit at a time, is such that the regions are defined such that the locality means that every time I take any kind of bit string x sub t in region A and I apply my transition matrix, I always have to go through B in order to get to C. And so if you have this kind of condition, then classically this is enough to get slow mixing. I won't show you the proof, but I'll show you like the quantum bottleneck proof eventually, so you'll understand this back just going on. But this is like a 3-line proof or so to figure out. Yeah.
How is this related to the notion of conductance in graphs? Is it sort of the same thing?
Yeah, so it's almost the same thing. Yeah. I think so. Like yeah, I think you can write it exactly the same way. So okay, I'm just going to write what I said in words there in case you want to read it. We've divided our bit strings into A, B, and C. B is exponentially suppressed or super polynomially suppressed, and any kind of thing in A to get through C, to get to C needs to go through B.
So like, what is the assumption? So far, these are just, you're assuming there exists a partition into ABC with these properties.
Correct.
And then so the last line is the conclusion. So like, then any local property.
No, sorry. These are all assumptions.
So far, okay.
So I'm assuming that I've done all these things. Okay. And then the conclusion is going to be yeah. Okay. Not next slide. Oh, there. I thought it was. Okay. So the conclusion is that your mixing time is at least a mega polyan.
Nice.
So in all of this, there's kind of a key thing that we have to define, which is the notion of distance.
Sorry, what's the distribution over which do you think? I can't read.
Sorry.
Like, is it pi beta?
Yeah.
That's a stationary distribution. Like, it's just a distribution. Okay, and somehow this says something about like the dynamic process running much.
The reason, well, let's prove the quantum thing. What?
Pi beta.
So it's the stationary distribution, any stationary for this thing to work. In our case, it'll be like e to the minus beta h. Classically, you can do e to the minus beta h of your bit string. It's Gibbs.
Sorry, like, what is this classical Hamiltonian doing in the whole setup?
it would be how the definition of pi beta is. I'm just saying that pi beta is a distribution, not a density matrix. So you don't need to write down Hamiltonian. You can just write down classical distributions, classical Markov chains to get this result. But I'm imagining that pi beta, the sub beta means that it's like e to the minus beta energy of the bit string.
Oh, okay. So it's like this classical Hamiltonian, it's like a function from bit strings to reals.
Exactly.
Exactly.
So okay, the kind of key thing to get this to work is we need to measure two things under Hamming distance here. We need to measure how far our matrix P can transition U. And in our case, we said you're only flipping one bit at a time. And so you have a set of neighbors where bit strings, we have a Hamming distance tells you that you can only move two things Hamming distance one away, bit strings Hamming distance one away. And then we have to measure our regions and say that to go from A to C, you had to pass through B. And so you also have to measure your distance between your two regions and say that that distance is larger than the how far your algorithm can, the range of your algorithm, how far your algorithm can step. So in the quantum version, we're going to need to generalize this. So here's the implication of the theorem. If my distance between regions A and C is larger than the range, as I hand-wavily defined it on the previous slide, of my transition matrix, then the mixing time is going to be at least the ratio of like support of A times support of C over support of B. So if B is exponentially small, you have an exponentially large mixing time.
The Markov chain is somehow like related to the Hamiltonian.
The Markov chain, it's the only things that you need are this locality and the fixed point at pi beta.
Right, but okay, pi beta is purely a property of the Hamiltonian.
Correct. And so
Okay, so then what does the Markov chain have to do? Like, what process are you lower bounding here exactly?
if you have any Markov chain that satisfies the two properties where it has locality and its stationary distribution pi beta, then I'm going to lower down its mixing time.
Ah, so it's also the stationary distribution of the Markov chain.
Yeah, sorry. So any Markov chain that has these two properties
It says the same.
Okay, so now let's try to make this all quantum. So I'm going to just replace my x t's with sigma t's. Now we have density matrices. We're going to replace our Markov chain with my Lagrangian, and we're going to replace support under the Gibbs measure with just support in the Gibbs state. Now we have to define distance and range. And for now, let's take my word for it that this sort of thing is going to follow. That's our hope, at least. Okay, so if you remember these A nu A's, those were kind of what I said are going to measure locality for us. Those jump operators with this Bohr frequency nu, since our Lindbladian is like a degree 2 polynomial on those, that will tell us kind of how far the range of the Lindbladian can go. And so the kind of immediate definition of distance that would generalize Hamming distance here is how many of those A nu A's I need to go from one state to another and have like a non-zero transition between them. So yeah, the distance between any two states can be defined as the smallest number of A nu A's I need to get a non-zero matrix element between those two states.
Sorry, so like, but this is gonna be a function of the sequence of these nu's as well?
Here you're minimizing over all possible sequences of A nu A's.
You can choose these nu's, but
Yeah, any path right through this set of operators. So this is great because, as I said, the algorithm is the algorithms we have are all degree 2, or we can say constant degree and have a slightly more general result. They're all degree 2 polynomials in the A nu A operators. So that gives you the range of the Lindbladian immediately. And then if you can just show that your regions are separated larger than the range, then we're going to have some kind of bottleneck result.
Sorry.
Yeah.
The Lindbladian is a map from density matrices to density matrices, right? So what does it mean to say that the range is 2?
So if I have I'm just referring, like, I can write it as a linear combination of range two things. The Lindbladian has these LK operators, right? And each LK is a sum of ANUAs. And so I just mean that I can decompose my entire Lindbladian operator. So it's acting, a single term acts with at most 2 ANUAs. Like if I have a state, to go from one region to another, I need to apply a string of many more ANUAs, then only providing 2, like it's linear in this thing. So only providing 2 is not going to transition me over.
You're not talking about a particular decomposition of L into cross operators. Or any decomposition into cross operators.
I see. It's enough to say that there exists a decomposition such that it is a degree 2 polynomial. Okay, so the nice thing about all of this is that if your regions commute with your Hamiltonian, then this is actually very easy to use because you can choose everything to be diagonal on the basis of your Hamiltonian, and that your ANUAs, if you recall, we had this nice definition in terms of eigenvectors. So this all becomes actually quite easy to use as a little crank that you turn. And so this is how we get out results for commuting Hamiltonians with very short proofs once you have this bottleneck lemma.
Does it become classical?
Yeah, it is.
Yeah, it's essentially a classical proof in this, but it's everything's
Everything's
diagonal,
diagonal.
which is why interesting results when it's not commuting. But there are some, I guess the existing results for classical things are slightly longer proofs. Like the existing proof for showing that good codes mix slowly is much longer. This makes it a very short proof, so it's kind of nice.
Sorry, like the distance you define is for 2 states, but then you said distance between A and C. Like, what do you mean by that?
Take the closest, so minimize over states in A and states in C, and then ask what the distance between those state size.
What do you mean stating?
Like minimize over sigma 1 in A, comma sigma 2 in C, distance of between sigma 1 comma sigma 2. Or psi 1, psi 2, maybe the pure states.
But so these A operators, they act on a whole, like, I mean, it's like a whole, like, levels.
Sorry, this is a region, this A is going to be a part of my Hilbert space. Maybe, is that the confusion? The jump operators are different from this A.
No, what I don't understand is like when you say state on A, like, what is that state in the rest of the system? Like, do you mean maybe an operator that is like identity everywhere else and then something non-trivial on A?
So yeah, in the quantum setting, A and C are going to be projectors, pi A, pi C. And so you'll have states there.
Okay, so then you have like a, okay, so it's just some projector on A and then identity everywhere else.
Yeah. Okay. And so, yeah, everything, as you said, is classical. So if you have a classical Hamiltonian, all of this turns into just Hamming distance. And so you kind of also immediately get this result that if you were mixing slowly when we used Hamming distance for classical Metropolis-Hastings algorithms, you're also going to mix slowly when you do this quantum Gibbs samplers. And so that's also our first theorem. Again, the proof for this is now very short and quite general. So now, if you have a random K-sat instance, or if you have a p-spin glass or something that is classically hard, I'd recommend not running the quantum Gibbs sampler. Okay. Any questions about? So this is all very nice for commuting things, but for non-commuting things, it's pretty tricky to use this definition. Because I need to know the eigenvectors of my Hamiltonian to do this. And if you give me like a random k-local Pauli Hamiltonian, I don't know where the eigenvectors are. I can't construct my regions A, B, and C and be sure that they're like, B is exponentially small. This is all very hard to use. So have we really done anything? I don't know. So let's try to write down a slightly different definition of distance that gives us a more tractable thing, but allows us to make the same sorts of arguments. So if you have a non-commuting Hamiltonian, here's a different definition, like locality-based definition of distance that you can use. So we're just going to say that in your Krauss decomposition of the map L, any Krauss operator acts on at most some number of qubits. That's what I mean by the locality here. And that's going to give us the range. And so this is going to work well for, as I said, these sorts of quasi-local Lindbladians acting on lattice Hamiltonians. So now we're just going to truncate and just, are you acting as an entity or not? And then the distance is just going to say, we're going to restrict ourselves to regions A and C that are defined over bit strings. And the distance here is just going to be the Hamming distance between the regions. And so everything is going to be done like forcibly in the computational basis. This turns out to be good enough for some Hamiltonians, like stochastic Hamiltonians. And it's good enough because it still says that if my region is, my distance between my regions is larger than the range of my Lindbladian, I won't be able to get a transition from A to C in one step. And so I'll be able to give the same kinds of bottleneck arguments that we had before. Okay, so this is like an easier definition to use. It's going to now allow us to do this transverse field Ising model business. So now I'll say the thing about locality that I wanted to say earlier. So the modern Gibbs samplers are defined, like the way that they produce the linear combination of A and U A's is by conjugating by time evolution the AA jump operator. And as a result, if your Hamiltonian lives on a lattice and you conjugate it by a time evolution operator, the time they evolved it for is constant. It's like beta. Beta is constant in our imagination. Then you can use Lieb-Robinson bounds to try to see how much is your operator going to spread. And what you find is that it's quasi-local, which means that you can kind of truncate it with epsilon error if you take it to have radius log 1 over epsilon. And so we can do this kind of analysis and just evaluate Lieb-Robinson bounds and show how large we have to cut it off. And so this is all kind of technically takes a while to do because bounding things takes a while to do. So we're going to ignore this from now on when I prove things for you, but it's something that we work out and make sure that nothing dies from this. Okay, so now I can tell you a kind of more formal statement, ignoring that quasi-local issue and just assuming that Lindbladian is actually local about bottleneck lemma. So I'm also going to simplify it a bit. Instead of having the Lindbladian map L, and we were doing like e to the LT to evolve under the Lindbladian map, I'm just going to imagine that we're evaluating a single discrete Gibbs sampler, this map T. And so instead of like, I'll just write it here, apologies to the people on Zoom, instead of something that looks like e to the LT of rho, we're instead just going to have this map T applied to rho. So that's why I apologize to people on Zoom. Yeah, I'll prove it for this kind of discrete Gibbs sampler where you just apply the same map over and over instead of exponentiating. It gives you kind of the same proof anyway. So ingredients are the Gibbs sampler applied T times, the Hamiltonian, and then I'm going to make our regions these projectors. They're going to be orthogonal, so a trace of pi A, pi B is 0, for example, and they're all going to sum to identity. We're going to make several assumptions. The first assumption is that our Lindbladian, or this map T, has a unique fixed point at rho beta. This is something I told you about earlier. It's not too surprising. I'm going to write the locality assumption now in this more general way. It suffices to say that the distance between your regions is larger than the range of the map under either of the definitions of distance we presented earlier. But I'm just going to write over here that it's like the map adjoint applied to C is contained in B.
A and C there on the right hand side.
No, it's B and C. So it's saying that if you just arrived in C, you must have come from either B or C. You couldn't have come from A. Right? Since we want to say that to go from A through C, you have A to C, you have to go through B. So if you just arrived in C, you must have come from either B or C, is what it says. Yeah, so in practice, when we do the proofs to show this property, we use this like distance and range definitions that I told you about.
Does it, because of the properties of the projector, does it also, is it kind of symmetric? Because you're not mentioning A at all, but I guess this, if this holds, it also holds for A. Or not?
Oh, like if I arrive, like is this of pi A plus A equal to B plus A? I didn't check. It doesn't matter for us. A mixing time is like a worst case statement where you just need to show that there is a state and like to mix from that state. It's worst case over the initial states. So, but that sounds.
I guess you're happy to make as few assumptions as you can.
Yes, exactly. It's a good question. I should check. And then we're going to need our bottleneck. So the bottleneck is going to say that our region B is super polynomially suppressed. Here alpha is some constant. And that trace pi A rho beta and trace pi C rho beta are both at least constant support. I really should have written pi A rho beta, comma, pi C rho beta, but I wanted to fit in one line, so I did A or C in subscript. So this we're going to have to show, the first two are kind of about the algorithm. This is now something about the Hamiltonian. You kind of have to prove it for your particular Hamiltonian that this is true. Classically, this is true for things like the random k-set, but doing that is already fairly hard. Like for any Hamiltonian, proving this could be hard. You have to be clever in how you find these regions A, B, and C to make sure this is true. We're going to do it for the transverse field Ising model. And then the last assumption we need is a sort of decoupling between your regions A and C to say that they don't have too much overlap under the Gibbs state in the sense of overlap. And so if A, B, and C and H are all in the same basis, then this holds trivially because I can just commute A past my my exponential and they're orthogonal, so this comes very easily. But in general, this is another thing you have to show. It's going to take some time for the transverse field Ising model, but I'll skip most of the details, so it won't cause you much pain. So if you have all these things, then we claim that the mixing time is at least super polynomial. So that's the statement. I'm going to prove it to you because the proof is actually very short. And we're going to use all these properties, obviously. So I expect you to commit them to memory so I can reference them on the next slide. Yeah.
So this means the mixing time to exactly the thermal state, right? But what if you, for example, allow some kind of like epsilon error or in traces sense to the?
So sorry, is the mixing time is to get like it's a characteristic time scale to get towards the thermal state.
Yes.
So after this time, you're not exactly at the thermal state. But perhaps you mean epsilons in like fixed point condition or other things.
No, I was thinking about like what if you want to go toward like something close to the thermal state.
I see. So you just use the in the mixing time, you're going to get like twice as close to the thermal state or something. So in twice the mixing time, you're guaranteed to get 4 times as close. So you can just use that. You're converging to a fixed point, like you won't actually hit it. So this just tells you how fast you're converging. Is that your question, or is that also not your question?
Yeah, you can go on.
Sorry.
The point is that you never actually.
Yeah.
This is the same class. You're in a Markov chain. You approach the stationary distribution.
Probably it's just a detail, but I'm slightly confused because in the last bullet point you write e to the minus bh, and in the one before you use rho b.
Oh, you could also normalize it.
Oh, that's the difference.
Rho beta is normalized by the trace.
Because if you put, so you could put the condition from the third bullet into, I mean, in the end, so this O of this trace is actually has to be exponentially small in. What's
I'm
the
not sure
difference
if-
between these terms?
He wants you to rewrite it in terms of rho beta.
Right, so you should did that somehow.
Right, so
We actually require this first term to be exponentially small. Does it imply?
no, I don't think so. I wrote it this way because it was all clear when I did normalization. But you could also normalize it and have essentially the same thing.
Okay, but he's asking like, since they are the same thing,
Are they the same thing or not?
are they the same thing? I mean, if they were the same thing, then your bottleneck condition would imply that this left-hand side of the last line is exponentially small,
Yeah.
right?
Let's see if I follow.
Like trace of pi b, the right-hand side of your last line, times e to the minus beta h.
Sorry, but these don't commute in general, so I can't get into that.
No, just
but
like,
just the right hand side of it.
just take the right-hand side. It's the same as like the very left.
Oh,
thing.
yeah, I see it. Yeah, sorry. I see. Yes, it's saying that this is exponentially small when you normalize it like you did. Okay. Let's try to prove the theorem. So we're going to define an initial state, sigma naught, like this. And I drop normalization, but it's just normalized by the trace again. We're now going to apply our map 2 times and see what happens. So let's first apply locality. This said that C was contained in B and C, like adjoint of T applied to projector C was dominated by B and C, so that we can show implies this, which is fairly intuitive. And then we're going to do this little t times. So I now have, pi c, my map applied to t minus 1 times. So I'm going to apply it to again. I pick up another b. And I also snuck in the second line is wrong. The third line is correct. I also snuck in the use of the fixed point condition. So sigma naught is less than or equal to rho beta in ladder order. And so by its CPTP map, property of my map, it's going to imply this last line. I skipped a few steps there, but I think it's not too hard to believe. I'm just
Doing the fixed point.
because I removed the map entirely. So just completely ignore the second line in your head. It's wrong. So it's not there. In the first line, we have this map applied to t minus 1 times. I'm just saying that the map applied to t minus 1 times for any t is going to be this is less than or equal to trace of I. Then the map applied to rho beta. And then I apply the fixed point to remove the map. So for those on Zoom, you just get there by and you pick up normalization. So
Backtrack to see, so I can see what fixed point said again, like.
yeah.
Oh, okay, like, okay, you have sigma naught on the left, and then you have like rho beta on the right, like what happened?
Yeah, so sigma naught is less than or equal to rho beta.
Why is that the case?
Because you can take sigma naught. Rho beta looks the same. When I'm saying I'm dropping the normalization factors, but I put it in the third line. So rho naught looks like e to the minus beta h. Sigma naught looks like that with a pi a. So you can take the square root. And you have a pi a instead of an identity there, and so you're going to get something smaller. So you apply the fixed point condition t times, and you get this last inequality. And then finally, you apply the kind of decoupled regions assumption to say that your first term here is smaller than is like the second term without the little t. And you have this statement that your quantity is ordered this. Then you apply finally the bottleneck, and your sizes of A and C were constant. The size of B was super polynomially small. You get a lower bound on your mixing time. So it's very short. What's the second?
It's kind of like you first wrote down what the argument you would like to be, and then you, for each step you made, wrote that.
It's also a very classical. I guess the classical argument looks the same, except you don't have this decoupled regions. That's the only thing that comes up because of this non-commuting Hamiltonian. But fortunately, we can show this property for something like the transfer field Ising.
The decoupled regions were about A and C, you know? So
Right, so A is hidden inside sigma naught, right? It's like literally pi c.
that you get rid of that term, basically, because it's exponentially small.
At least as small as
okay. As B. So it's multiple.
yeah. And to answer your normalization factor question earlier, this inverse trace of pi a is the normalization factor that pick up, but it's constant size in our thing, so it's the same as saying exponentially small. So now let's try to apply this to the 2D transverse field Ising model. Here's the Hamiltonian. It's just you have a 2D lattice. I'm going to make it root n by root n. And you apply zi zj on any adjacent vertices on the lattice. And then you have a transverse field with minus h sum of I xi. This is the paramagnetic transverse field Ising model. So how do we, yeah, go ahead.
I understand the rotation, like the two i's, they range over different things, right? It's like the first I ranges over a set of square root of n elements. Second I ranges over all of the n qubits.
Correct. Yeah, the angle brackets indicate neighbors on the lattice. And the other one is just a sum of all terms. I always like using I for two things at once. I think it makes life more interesting. So
But it's like a quantified variable, so it's fine, right?
yeah, but I should have written the limits to the sum. I should have written the limits to the sum to make it clear. So there's a nice tool to use for all of these kinds of stochastic Hamiltonians, where you can write down like a path integral Monte Carlo, so some people call it. I think the traditional name might be Feynman-Katz. And what you do is you take e to the minus beta h and write it down as a probabilistic process, which I'm going to make clear for you here at the cost of some math. So what you do is you tronerize it in a very convenient way. It's a common trick, so many of you might have seen this before. You take the part of your Hamiltonian that's diagonal in z, the part of your Hamiltonian that's diagonal in x, and you divide these up into your two trotter terms. But then you add and subtract the identity, such that your thing that's diagonal in x looks like the the rate matrix of the continuous time Markov chain. So all of the sums row to 0 and all of the off diagonals are the same sign. And so this allows you to write this nicely as a probabilistic process, because you can diagonalize the first term trivially, it's already diagonal. And then your second term is just going to correspond to some kind of spin flipping process. And so for the transverse field Ising model, it's very easy to write down what this does. If I write down my computational basis states as like spins in plus minus 1 in the kind of vicious way, you can write down any matrix element in the computational basis of your thermal state in terms of this Poisson process, where I have some random Poisson point processes and I of t that are just like proceeding up the positive line. So it starts at 0, and then it has at time t, the value of ni of t is like Poisson distributed with parameter beta ht. And you condition on the fact that when you run your path, you go to sigma prime from sigma. You can also write it the other way, it's symmetric. And so this gives you a very kind of good handle on how to compute quantities, because now you can write everything and just evaluate expectations of your Poisson processes. Sorry, I see like
H, the rate in the rate.
yes, in the definition of the Hamiltonian.
Okay.
Yeah. So this allows you, to compute many things. Of course, doing this computation, you can run it on the computer. But if you want to do it analytically and try to prove things, you have to kind of have enough structure over which sigma and sigma primes that you're evaluating on. And so a lot of the proof is just trying to find configurations that you can show bounds on. So this is a very useful trick to have in the toolbox, and it applies here to show both of the things we need, the decoupling assumption and the bottleneck assumption. The bottleneck assumption is done basically the same as classical proofs. So classically, you can show the 2D classical Ising model mixes slowly with this kind of fault line and parallels-like argument, which I won't get into because it's basically the same as the classical argument, and I only have a few minutes left. And so the more techniques have to be done for showing decoupling region. And there, what we do is not actually, but morally, basically what I wrote here, where what you do is you take your Poisson process and you can think of it as running an imaginary time. You just discretize that into small time steps and then union bound over those time steps. So if you just take this from like a quantum info perspective, I'm just saying you bound the Trotter error essentially and evaluate each Trotter step of that exponential. When we do it, actually, we don't use Trotter error bounds because there seems to be a shorter way to do it, but that's essentially what's going on. Okay. So I think that's all I'm going to say about the methods of how we get to the transverse field Ising model result. But here's the result, roughly speaking. You can choose any temperature below some constant and any transverse field strength below some constant. You're going to get slow mixing like e to the root n on a root n by root n lattice for the transverse field Ising model in the ferromagnetic phase. So this is nice because at least we've seen now that this kind of bottleneck lemma that we've developed can tell you mixing times of Hamiltonians that people previously had trouble getting mixing times with kind of other techniques. So it seems like this generalizing this kind of clustered picture of a bottleneck maybe brought us somewhere. So I'm going to end with some open questions now. The first kind of obvious question to ask is, I showed you this nice probabilistic interpretation for stochastic Hamiltonians. We can produce these probabilistic processes. But if I gave you something like a random k-local Pauli-Hamiltonian, I still have no idea how to do this. Like, can you write down the notion of distance, or are our notions of distance good enough to show bottlenecks? So if you have something that looks more like a quantum spin glass, it is not kind of semi-classical in the stochastic sense, then these techniques are quite hard to use as far as I can tell. The second question is one that's more practically applicable. Mixing time is defined, as I said earlier, as like over all sigma and sigma prime, they converge. So it's a worst case statement saying if you have the worst initialization possible, how quickly do you mix? But in practice, you're probably going to initialize from a product state or from maximally mixed state or something simple, and then run your algorithm. And the bottleneck arguments are not going to prove anything for you there. Classically, this is also a very hard problem. We can't even classically say, like, if I start from a random bit string, how quickly do I converge? It seems that's also much harder to analyze than these worst case mixing bounds. So it's a question, though, that I think is probably more valuable to people who have a quantum computer and want to run stuff on it. And then the last thing, which I'm probably the most excited about, is trying to see if these same kinds of ideas can be applied to things outside Gibbs sampling. Because in the classical world, there's this whole community of people who work on lower bounds that match stable algorithms. You have all this like literature on trying to match approximate message passing and get kinds of these transitions where you go from easy to hard to impossible. And showing where these transitions lie often relies on arguments like this. They're conjectured. It's more like a physicist thing to do, but they rule out all stable algorithms and then hope that that's tight. And for many tasks like random CSPs, this is as tight as we have. It'd be nice to generalize those sorts of results to the quantum case. The only algorithm that I could think of when trying to come up with like how to make a quantum version of the overlap gap property was Gibbs sampling. And it seems to have produced some result here. So I'd be very curious if there are other families of stable quantum algorithms that where you perturb the input a little bit means your output changes by a little bit, essentially. These sorts of algorithms can produce lower bounds by a similar kind of bottleneck or clustering picture. And yeah, I think that's an interesting idea that hasn't really been explored too much by the community. So I'm going to end there. Thanks.